Hi, I'm Thomas Ulrich, and with Alice Gabriel from LMU, we've been working on studying the scale-dependent fault roughness effect on earthquake dynamics and ground motion. Numerical models of earthquakes on Ross fault can generate high-frequency ground motion that resemble the ground motion observed in nature. And here we are interested into see whether or not there's some scale wavelengths that affect more the earthquake dynamics than others. So we use SCEC, which is a dynamic rupture solver, and we use Ross fault of 50-kilometer long and 15-kilometer wide with a varied process zone width. So the process zone width is length scale over which friction drops during an earthquake, and varying also the spectral content of the Ross fault, so we can study these effects. And yeah, the first part of this study is about changing the process zone width and looking at the simulated ruptures. So in the framework of a linear slip weakening law, we can vary the process zone width using DC, because it is proportional to DC, it is a rupture process zone width. And so we change DC in 4 different values from 0.5 to 0.1. And then we also change the press stress to get the same overall characteristic of the rupture, that is duration, magnitude. And you can see here the simulated rupture, which are less coherent at large DC than at short DC. So there's really a dependence overall of the roughness effect on the rupture process zone width. So that's one of the first message. And then we study some source properties, in particular in terms of their distribution in all these models. So the fault slip magnitude, the rupture speed, the peak slip rate for decreasing DC. You can see that the fault slip magnitude is very similar, but on the other hand, the rupture speed is much more incoherent for large DC than short DC. The peak slip rate increase with decreasing DC, which is expected because we want the same amount of slip and in a shorter duration. So then the peak slip rate has to be higher. So then we study the spectral characteristic of these source properties. So this is the amplitude spectral density of the peak slip rate against a normalized inverse wavelength. That is the wavelength, the inverse wavelength times the process zone width estimate. And you can see that there's 2 slopes which suggest a critical behavior of the fault roughness effect on the process zone width length scale. On the other hand, so we look also at the spectral content of other rupture characteristics, that is the rupture speed or fault slip, and they are consistently fractal over all scales. So this critical behavior is not intrinsic characteristic of fault roughness effect. So based on this first part, and because the choice of the minimum wavelength of the roughness may impact strongly the numerical cost of Ross fault simulation, we propose a hybrid approach in which fault roughness is meshed to a given wavelength, which is lower than the process zone wavelength scale. And the small scale geometric features are approximated by traction heterogeneities. And so we want to see if we can emulate the full dynamic behavior with this kind of model. And the response is yes, if we scale the fault strength accordingly. So this is the reference model, and this is a hybrid model. So they are looking very similar. On the other hand, when we look at the source properties, we see that some of them lack of small scale heterogeneities. And this may translate into less realistic ground motion. Therefore, in the last part of this study, we study the ground motion of this model. And we see that the ground motion generated by the reference model are very similar with the ground motion from the hybrid approach. So this is a spectral acceleration at 9 Hz. And here you can see the decrease of the average spectral acceleration at different frequencies against the distance, and the curves are matching each other. So altogether, this study advance of understanding of fault roughness effects and should allow more efficient hazard characterization using physics-based methods.